Okay, can you just tell me my voice and everything is okay? Is it working fine? Okay, can you just tell me my voice and everything is okay? Is it working fine? Okay, can you just tell me my voice and everything is okay? Is it working fine? Okay, can you just tell me my voice and everything is okay? Is it working fine? Okay, can you just tell me my voice
Okay,
and
then,
everything
so
is
let's just
okay?
start with the today's class. In today's class, we're going to discuss
Is
about
it
the
working
E1 and
fine?
E2 mechanism there, okay?
Okay, can you
Okay.
just tell me my voice
So, okay,
and
then, so
everything is
let's just
okay?
start with the today's class. In today's
Uh,
class, we're going to discuss
is it
about as
working
we
fine?
already discussed in the previous class, we
Okay, can you
discussed
just tell me
about.
my voice
So, okay,
and
then, so
everything is
let's just
okay?
start with the today's class. In today's
Uh,
class, we're going to discuss
is it
about
working
as we
fine?
already discussed in the previous class, we
Okay, can you
discussed
just tell me
about.
my voice
So, okay,
and
then,
everything
so
is
let's just
okay?
start with the today's class. In today's
Uh,
class, we're going to discuss
is it
about
working
as we
fine?
already discussed in the previous class, we
Okay, can you
discussed
just tell me
about.
my voice
So, okay,
and
then, so
everything is
let's just
okay?
start with the today's class.
Hello, am I audible?
Hello, now it's okay. Hello, am I audible now? Still the same problem, voice is not clear. Okay, then, so let's start now. Already we so much time, right? So yes, let's start with the class. As we already discussed in the previous class, we are going to start with E1 and E2 mechanism is there, okay? So in E1 and E2 mechanism, so as we already discussed about alpha and beta, so in the beta one, we are going to discuss about E1, then E2, then E1CB, and then further that is EI also there, okay? So these are the things we're going to discuss basically in today's class there, okay? So Yes, regarding the session, listen, my point that is there is just so many session left. Okay, it's not like I'm only covering the haloalkane and haloarene. We are basically discussing each and every topic. Like this E1 and E2. Okay, like this E1 and E2 mechanism is basically the part of the previous class. Okay, so like reaction intermediate is the topic there, but yes, we are going to discuss all these things today there. So let's start. I'm sorry for all the technical problem. Now let's start with the class. Any problem if you are facing, please let me know. So E1 and E2 mechanism we are going to discuss. So in the previous class we already discussed about alpha and beta mechanism, if you remember, that some living group is connected with some carbon and this is going to be the alpha, and with respect to this the next carbon is going to be the beta there. Okay, and further it is going to connected with more carbon is there. So if the living group release from this side, it is going to be the alpha. But on the other hand, if let's suppose this is some hydrogen is there, and if this hydrogen participate here, so it's become alpha and beta. So in today's class the topic of discussion is only going to be the beta reaction have to be there. So you can say E1, E2, E1 CB and EI there. Okay, so let's start with the very first E1 mechanism there. So if you remember the same SN1 mechanism, so E for elimination. If let's suppose we are going to discuss about, so E for elimination, it is simply representing that elimination reaction there. Okay, so it's a elimination. And one for unimolecular, E for elimination and E for unimolecular reaction there. So it's a unimolecular elimination reaction have to be there. Okay then, so it means the same like the SN1 mechanism, it is going to be the simple first order reaction. Yes, you're right. So let's see the definition wise what is the meaning of this word E1 mechanism there. This is definition that here the first living group leave the substrate. Okay, like the previous cases, if let's suppose we're typically talking about, first of all, let's suppose there's some kind of living group. Let's say this is X is some living group, and this is my carbon, and this is the hydrogen, this is the hydrogen, this is the hydrogen there. Okay, so simple. What is going to happen in this case, that first of all this living group leave, and then there is a formation of carbocation take place. So like the SN mechanism, it is like behaving like a formation of carbocation is the rate determining step there. Okay, so this is written here. Let me just again moving there. Now observe this. First of all, the living group leave the substrate. It means there is a generation of carbocation, and then the proton attraction take place from the alkene part there. Okay, so what is the meaning of this word attraction is there? It means this is some negatively charged, and then there's some kind of base came to the picture. Look at this. This is my some base, and this base simply attack here, and this side is an like attack here. It means at the end we are end up with alkane. So this is the main agenda in this case, that basically we are dealing with the alkene system there. So observe this, carbocation formed as an intermediate, and the proton if section take place to form an alkene there. So this is a simple reaction, you can say definition wise it's a E1 reaction there. Now the question, like in organic chemistry, which reaction follow the even mechanism? There is any kind of particular reaction? Yes, there's this two reaction basically. Although like sometime we are getting different kind of mechanism, but yes, observe this. There's a two example here. First of all, it's a dehalogenation of alkyl halide. Okay, see, I said dehydrohalogenation. Can anyone tell me what do you mean by this word dehydrohalogenation? We discussed this so many times. Yes, please. Anyone? What is the meaning of this word that is dehydrohalogenation? Yes, anyone? Okay, see, hydro means, please be noted, hydro is not really the water, right? So basically, in this case, what is happening there? That hydrogen plus halogen. Okay, hydrogen plus halogen, two things is going to leave that hydrohalogenation. Okay, see, it's obvious. Observe this. If let's suppose this is some X is there, you know, X is living and plus hydrogen is also living. So hydrogen plus X is living. So water can't be there. Okay, hydro means hydrogen. It's represent hydrogen. Okay, second is going to be the dehydration of alcohol there. Okay, so maybe dehydration, what everyone is familiar. If you remember in the previous class, we discussed about this. If let's suppose I'm having a five-member ring and there is some OH group is connected. If you remember the last question we discussed, there is this OH part. Okay, means dehydration of alcohol is there. So now let's start with the very first part, that dehydrohalogenation part here. Okay. Yes. Hi, Sidhu. Yeah, you're right. So let's see that how to discuss about this. First of all, we're going to discuss about a dehydrohallucination of alkyl halide. So let's discuss an example. Example is there. So let's just talk about an example, very simple example. If let's suppose I'm having some carbon and this is some halogen is there, this is one more carbon and one more carbon, okay? And let's see some hydrogen group is connected here. So in this case, let's see we are using some base as well. So basically what is happening, this base abstract the hydrogen and this is the living group, it is going to leave, okay? So basically in this case we are getting that if we are going to discuss about the reaction, carbon, carbon, carbon and double bond carbon have to be there. Okay, it means HX remove there. So it's known as a that D hydrohallucination reaction. Don't worry, everything we are going to discuss in very much detail, mechanism wise and everything. Okay, so let's start with the real point, that is mechanism of the E1. Do you know mechanism of the E1 basically follow a two-step reaction? How about the two-step reaction? Obviously, the first step is going to be the formation of carbocation. The first step is going to be the formation of carbocation, and do you know it's a rate determining step? Okay, there is a carbocation formation take place, and it is a RDS step, means rate determining step. It's a simple rate determining step have to be there. You can say slowest step. So let me just write this RDS here so that you are able to understand. And the second step is what? That removal of proton, you can say, okay, hydrogen, proton, but you like, you can use there, okay. So in this case, the second step is going to be the removal of hydrogen. Okay, removal of hydrogen, simple sorted is there, okay. Let's see how to proceed with the step. So there's a total two step is there. The step number one is the formation of carbocation. So look at this I is some living group, as we already discussed in the previous classes that halogen families most of the time behaving like a living group. So this iodine is going to live. It's a slowest step, it means it is a rate determining step. Obvious, this reaction follow more than one step. It's a complex reaction, and if it is a complex reaction, so it is going to follow the slow step. Two step, it means the rate determining step is the slowest step. So it's a formation of carbocation. And okay, it's a very good question, like can you just tell me the rate then? What do you think about the rate? If formation of carbocation is a rate determining step, if RDS is the you can say formation of carbocation is the RDS step there, so what do you think about the rate of reaction? Wait, I will give you some kind of example as well. Okay, so you to range them in order of rate of reaction, okay. So this is the case number 1, A. This is the case number 2. Okay, like this, B. And the next one is going to be the, yes, please. What should be the order here? A, B, O, C. Yes, please answer this question. Okay, I will tell you this reason as well. Just wait for a while, okay, Mayank? Why it's leave? Yes, please answer the question. What will be the order A, B, C? You said A, C. Okay, Mini. C, B, A. It means so much variation, right? Okay. You said CBA. Okay, Aditya. Are you sure, Aditya? Okay. So in this case, observe. If let's suppose this X is going to leave, okay? If this X is going to leave, this X is also going to leave, and okay, this is already a carbocation. So in this case, if it is going to leave, this is the positive charge here, and in this case, the positive charge here. Okay, let me just write it properly, like how it is going to behave. So for example, this is some carbon, and it is being like you can consider it's removed already. So let me just raise this hydrogen. It means the after the removal, what is going to happen? This carbon we discussed in the previous to previous class. It's the carbocation has a vacant space, right? That one more remove this hydrogen, okay, like this. And then what is going to happen in this case? Obviously it's a benzene, and benzene is what? Benzene has a double bond. So you know what you're observing, these double bonds start participating in a resonance here. If it is participating in resonance, so obviously it is lead toward the stability, right? And how about the second one, that if you to observe again, it is a allylic one. If you don't know, be noted that every time allylic or benzylic, okay, it's allylic carbocation and it's benzylic carbocation. So do you know, as benzylic and allylic carbocation is really very stable there. Okay, and then if you to observe this, is it secondary or primary? I guess there is a no point of discussion for the option number C. C is going to be the last one, right? Is it secondary or primary? Okay, so yes, if you to observe this carbon, it is connected with one carbon, two carbon. It's a secondary there, okay? It's not tertiary. If it is tertiary, maybe the problem will be there, ma'am, how to identify, but secondary. So what is the correct answer for this question? That is A, B, and C. So this is how we are going to follow the order there. Yes, Sanjana, you're right. Okay, now the next question is there, that why it is going to leave. Okay, so yes, let's discuss about this point, like what is so special about, like why it is going to leave there. Okay, my simple question for you, if this is carbon, it is connected with halosine, okay, and this side some nucleophile, let's say OH group is there, okay, this is negatively charged, and okay, like this. So yes, Mayank, can you just tell me who's going to connect with carbon first? Is it O or is it halogen? Let's just say, like we are discussing so many times, this is iodine, right? So yes, what do you think about it? Like why iodine is going to leave and OH is going to connect? I will tell you. Wait, okay? Yes, Sanjana, wait. Yes, please answer this question. You know, carbon be like it's belong to the 2p, you know, it's a second period element, and iodine is what? Iodine is belonging to, if you can consider fluorines, the 2p there, and then it's chlorine, it's going to be the 3p, and then we are dealing with the bromine, it's a 4p, and iodine is what? 5p there, it's a 5p. Okay, so you know, so many times we discuss about this, that first of all, living group have to be very good there, and the second very much important point is what? That upcoming group have to be very good nucleophile. Okay, so in this case, this OH is a very good nucleophile. Nucleophile means donor. So iodine be like, no, I can't comfortable with you. OH come and iodine just leave the molecule, and hence this is the reason. Do you know why the reaction is going on? In order to achieve the stability, Mayank. So that's why simply, in order to get the stability, in order to achieve the stability, the thing is going to happen there. Okay, so just wait, again we're going to discuss about all this thing, like why something is leaving, something is coming there. Okay, this is also, there is also the reason there. It's not like everything is just happening just for a while. Okay, no, everything has a reason. Okay, so yes, what we're discussing, why the second B is the correct one there, right? So you know, resonance, Sanjana, that if we are talking about the resonance part here, let me just like, move again. So how about the resonance? In this case, this is a double bond, and you know, this carbon is positively charged. Again, it is a vacant, right? And what is happening in this case? This double bond simply move here, and basically we are end up with double bond like moving this way, and this is a positive charge. That's it. This is how it is happening. Okay, so you know, when we're talking about the Ahari rule, so we discussed this thing so many times, that first of all, you know, mesomeric is nothing, if you know. Okay, that mesomeric is nothing, let me just write here, maybe it's not visible. Mesomeric is nothing, that simply the resonance. So mesomeric resonance effect is always the dominating over the hyperconjugation and then inductive effect. If you're to back here, let me just move toward the question part again. If you to observe here, you know, these group behaving like a plus I, and if you to compare which kind of effect is there, plus H, you know, hyperconjugation, alpha hydrogen. But in this case, that what is the plus point? Resonance have to be there. So according to the order wise, allylic is more stable over the normal secondary. Here this is only secondary, it's not tertiary. Okay, are you getting, Sanjana, this point? Okay, I hope you are getting now. My voice is low actually. See, what is the problem when I'm using my headphone? So like I'm not able to listen anything. Okay, so I guess it's clear now, right? Just let me know it is okay now, Diksha. Next time I need to use the earphones. Okay, maybe it will resolve the problem. Wait, okay. Okay, so is it fine, I guess, right? So let's continue anyway. So let's discuss about the step number two. That is the second step have to be there. So how about the second step? That is attack of the base. So now positive charge is already present. Now the next step is going to be the what? That removal of this hydrogen there. So observe this. This hydrogen simply taken by the base. So what is water? Water be like I'm having a lone pair, so hydrogen just come with me. So simply this hydrogen move there and there is a formation of double bond take place and water form. So it's a two-step reaction. The step number one that is a formation of carbocation. The step number two that is attack of the base there. Okay, don't say it's a nucleophile. It's not nucleophile. In the previous class, we discussed about this point that if you to compare between OH and a water, so OH is a very good nucleophile. Water is not a nucleophile. Water is a base. You know, something is very good base is may or may not behave like a very good nucleophile. So it's a nucleophilic order. We already covered all these things earlier. Okay, so it's a very simple there. So if we're talking about the rate there, so let's just back on the slide. You know, it's a slowest step. It's a rate determining step. So it's going to like simply determine the rate of a reaction there. So let me just write the rate of a reaction. So in this case, do you know the rate of reaction is equal to the slowest step there? So in this case, the rate of reaction depend upon only one thing. This is, you can say reactant, or you can say it's a substrate there. So this is my substrate, okay? And raise with the one power, okay? Because we are using only one thing there. So let's discuss about the rate of a reaction. If we are observing, this is a rate of reaction. That Rx raised with the power 1 and base raised with the power 0, the rate determining step of a even reaction involve the formation of carbocation. Okay, so that's it. This is all for the simple mechanism. If you already know the SNU mechanism, so it's almost similar. What is the difference between this and there? Here we are dealing with elimination and there we are dealing with the substitution there. Okay, simple. This is all for the mechanism there. So now let's discuss about the stability of carbocation. Okay, so as we just discussed already that how about the stability of carbocation there. Okay, so let's just discuss about this quickly, that if let's suppose I'm having a tertiary carbocation, this is my tertiary carbocation. You know, tertiary is there. So in this case, basically what you are observing that one, two, and three. Three electron donating group connected there. So one, two, and three. So tertiary is more stable, right? And second is going to be the secondary. That this is CH3 and this is CH3 and this is some hydrogen there, so it is secondary, it's a secondary carbocation, right? So it is more stable because in this case only two group is connected there. Next is going to be the one more, that last one, primary, how to be there. Okay, and still it's a request, if you don't know how to identify primary, tertiary, and secondary, please ask me there. Okay, and yes, this is all for the stability, that tertiary is more stable or the prime secondary is more stable or the primary. Now this is all for the stability order of a carbocation. Now let's observe this dehydration of alcohol. Okay, so how about the dehydration of alcohol? Let's just discuss a question. Okay, a kind of example, not you can say question. So how about the example there? So let's discuss about a question. Observe this. First of all, this is my phenol. Simple phenol is there. Okay, and in this case, okay, we are using H positive ion. Okay. So yes, what is happening in this case? What is the product? Answer, sorry, questions, sorry, options for you. Option number one, this, this. Okay, wait. And then D, D, D. Okay, D is there, none of these. Yes, please. No, Mayank, see, listen my point, okay? You are not getting, listen my point, everyone. What we are dealing with elimination reaction. Okay, Mayank. So listen my point. First of all, there is a removal. First of all, there is a removal of normally the living group. Okay, so in this case, if let's suppose we are talking about dehydration there, okay, let me tell you the first step. This is how really it's going to happen there. This oxygen has a lone pair, you know, and this oxygen connected on this hydrogen. Simple. Okay, what we are getting basically that in this case, this is my O group and it is connected with hydrogen. Hydrogen, it's a positively charged. So right now it's not behaving like a nucleophile. It's right now it's not behaving like a nothing. It is here simply behaving like a living group. Okay, it is going to live at the end. So in this case, if let's suppose I'm using this, this is positively charged. Okay, this is the step number one, formation of carbocation. Okay, and after the next step, what is going to happen there? If let's suppose I'm not using any reagent from outside, although let me just mention some base have to be there. Okay, this is some base. If base is not present there, so what is going to happen? We just discussed water is also behaving like a here, that is base. Water is not behaving like a nucleophile. If water is behaving like a nucleophile, it is going to be the you can say which reaction, that substitution reaction. Wait, let me just give you an overview actually what is going to happen there. Okay, okay, so listen my point that actually what is going to happen in this case. Observe this. Just try to understand the scenario. First of all, I'm having OH. Okay. So in this case, the first step is going to be the formation of carbocation. Now the second point start. If let's suppose water is behaving like a base, so what is going to happen? Obviously, the water is going to abstract this hydrogen. Okay. So what we are end up here, that is double bond. So this is elimination reaction. It is elimination reaction. But if let's suppose the same water is behaving like a nucleophile, so what is going to happen? This water connected here again. It means what is happening there, that water is connected here. So what is it? It's a substitution reaction. We discuss that OH is replaced by the water. Okay, and it's an elimination reaction. So listen, what is the basic difference between substitution and elimination? In elimination reaction, okay, we are requiring a good base. We are requiring a good base, but for the substitution reaction we are requiring a good nucleophile. Just wait for a second, or like for this class only. In the next class we're going to discuss about like how to select which one is a very good nucleophile, which one is a very good base, because in the next class we're going to discuss about how to differentiate between a nucleophilic reaction or a elimination reaction. Okay, it's okay, now we are dealing with elimination, but same question, if let's suppose I will write there is a OH negative and SH negative, right? In the previous class we discussed both are a very good nucleophile, but which one is being like a base and which was being like a nucleophile? This is the important point, right? In the previous class we discussed about if you're using SH, it is a very good nucleophile, which is a bad if you're using polar solvent. And solvent also play important role, Mayank. Okay, so I hope you are getting actually what is going to happen. So just for this class only, let me just give you a very simple basic funda. Listen, it's work everywhere. What is the main important point here? That water is a base. Water is a base, but OH is a nucleophile. That's it. If water present, definitely elimination reaction have to be there. Okay, Mayank, I hope the basic difference is clear for everyone. Like, what is the main agent of the class? What is the real meaning of elimination? Right? That actually really what is happening. Okay, so let me just back there what we are discussing. That question, right? So, where's the question? Question, okay, yes. So, what is the correct answer for this question then? Okay, very good, everyone. Option number A, D or B. Dear me, no, no. See, look at this. It's already, in this case, it's already a water, right? So this hydrogen is there, water is going to connect here, this bond open up, and what we are getting there, that option number is going to be the correct answer. Okay? Is this point clear? Okay, cool then. So let's continue further. This is all for the case. Let's solve a question, everyone, okay? Please solve this question. Question asks the amount which will give the most stable carbocation on a dehydration. So is it really funny? Yeah, anyway, answer the question. Same type of question. Take your time and answer the question properly. And please be noted, if we are checking for the stability, so it's not like, ma'am, that you can say migration have to be there. Rearrangement we're not talking. Be noted, everyone. Rearrangement we are not going to consider. It's very much important point. Okay. B. Okay, so yes, definitely everyone is right. Option number B is going to be the correct. Why? Let me just remove this. So this is my this carbocation, right? If you to remove this, this is this carbocation, and if you to remove this, this kind of carbocation we're getting. If I'm removing this, this kind of carbocation we're getting, right? So let's just see that which one is behaving like a primary or secondary. So in this case, this carbon connected with only one carbon. So this is simply primary. This is simply primary. How about the second one? If you to observe this, this carbon is connected with one carbon, two carbon, and three carbon. So it's a tertiary. And in this case, it is connected with only one carbon. So it's a primary there. And if this is connected with one carbon and two carbon, it's a secondary there. So secondary, primary, primary, and only option number B has a tertiary carbocation. And we just discussed the rate of a reaction, right? That's it. This is all for the case. Now please make a kind of note what we are discussing. Basically, first of all, the definition of even. Okay, then the next one is the like example, that first of all, the dehydrohallucination. The next is going to be the dehydration of alcohol. Then the rate of a reaction, like tertiary, secondary, and primary. And next topic is going to be the thermodynamics. Okay, thermodynamics. So let's quickly recall the thermodynamic there. So what kind of thermodynamic? What we are really dealing in a thermodynamic. So that's simple. Which one? That chemical kinetics. So how to draw the graph that thermodynamic? Just wait. Everything on the next slide. I'm just giving you an overview there. So first of all, that this side you are having some kind of potential energy. Okay, and this side we are having a reaction coordinate, or you can say progress of reaction simply. Let's quickly recall the Arrhenius equation. If you want to convert a reactant into the product, like chemical kinetics, so you have to follow that this kind of barrier. Activation energy is the name. This is simple. I'm talking about the general case. It means reactant, if want to convert into the product, that reactant is lie something in between them as well. Activation energy achieved that, and then reactant is further moving toward the product side. Okay. Now, in this case, we just discussed that thermodynamic, what is really happening there, the even mechanism follow two step. The step number one, it means the formation of carbocation, right? Formation of carbocation. And the second step is what? That is removal of protons, a two-step reaction. It is a two-step reaction. It means in this case, we are end up with two kind of thing. Okay, so let's quickly try to draw this, like how it is going to form. So let's just discuss about a very much important point, that how to proceed further. Okay, so let's see, this is a reaction coordinate this side, potential energy and reaction coordinate. So what is happening there? You are having some Rx, okay? Rx is simple, and it is converted into the, it's a slowest step. Okay, so if it is a slowest step, so how the graph look like this. I will tell you how to decide. Okay, maybe you are not getting. Okay, so in this case, this is how the case. It's a product there. Okay, most of the time the product like below there. Why? What is the reason there? Because see, this is a product line, and see, this is a reactant line. We know why the thing is going on, because obviously the reactant product is more stable over the reactant. That's why reactant above, product below. And if let's suppose we are talking about the like is it exothermic or endothermic reaction, so there is a the line in a negative direction, it's like to a zero, and it's a like below the zero, so it's a basically a exothermic reaction. This graph simply representing a exothermic reaction there. Anyway, leave that. So what we're discussing again, it's a two-step reaction. The step number one is what? Rx is going to convert into the R positive. Okay, so it means from there to there, the step number one is going to happen. It means the generation of R positive take place. Carbocation take place. Okay, so this is simple thing. This is a step number one. Let me just remove all these things. So it's a R positive there. And what is this? This is a transition state one. It's a transition state one, TS state one. We already discussed this point in the previous class, if you remember. It's a TS1. It's a transition state one. It is a transition state one. And what is it? It is an intermediate. It's an intermediate. We discuss about that carbocation and carboanion and free radical are the intermediate. Okay, then. And further, it is going to be the TS number 2. Okay, that is transition number 2. What is the difference between the transition state and an intermediate? You can say the lifetime of intermediate is more over the transition state. Okay, yes, both are like imaginary thing, both are like not technically stable. Okay, this is just like a imagination. Once they quickly form, they quickly remove. Okay, So that's it. It's a TS1, this is TS2. And again, let's connect it this with the nucleophilic substitution reaction SN1. There we discuss about that what is the relation between intermediate and a transition state. That this is the relation between intermediate and transition state. Intermediate state is equal to the transition state minus 1. Okay, like in this case what you're observing, basically there's a two transition state, right? But if we're talking about only the simple intermediate, so it's only one. So transition state 2, yellow one, and intermediate only one there. So it's a formula. Yes, sometimes the question asks from the formula like what do you think about transition state, and if let's suppose this is the number of intermediate, right? So it's a most commonly asked question sometime in a paper. Okay, like maybe not direct question, like maybe the statement frame be like a reaction is going on there, we're getting three intermediate, so how about the transition state? Okay, so this kind of question frame. Okay, now the next point that we just discussed, the first step is going to be the rate determining step, right? Rate determining step. So, like you can say it's a slow step. The step number one is a slow step. But why it is a slow step? Come on, see the activation energy. If you have to observe the activation energy in this case, what is the activation energy? See this. The first one, let me just highlight this. Okay, yes, this one. It's pink one, okay? I'm talking about this. And how about the second one? Look at this one. Which color? Okay, yes, orange one. See this. You know, if you have to compare between the activation energy of this that pink one and this orange one, what you are observing? Pink one is more. So wait, activation energy more, rate of the reaction is slow, yes. So the first step, the formation of carbocation is the rate determining step is the slowest step. Yes, it is the slowest step. Okay, so that's it. This is all for this point. I hope this graph is clear for everyone. And again, it is a copy and paste part of the SN1 mechanism. Okay, as we'd already discussed earlier. So that simple is there. And if you want a very good graph, like how the graph really look like, this is how the graph look like. So what does this graph simply represent to us? That here there is some kind of reaction is going to happen. That first of all, this bromine is going to leave and breaking of CBr bond. Slowest step, formation of carbocation. So the graph from there to there simply representing this. It is some kind of reactant, and this is my transition state 1. Why, what is the meaning of transition state? A state where no bond form, and you can say some bond are breaking and some bond are forming. So this is the stage where the bond is not completely break, they is about to break. Like bromine is about to leave but not completely leaving. And at this point the maximum height, the maximum energy achieved and quickly converted into the intermediate. Okay, so it's an intermediate formation take place. And further if we are moving again, and this is the second step, that is the loss of the proton there. It's a two-step reaction. This is how the graph look like for this. You can say the thermodynamic is there. Okay, so after this thermodynamic, I guess so much time. Yes, please. Any problem if in the graph anything, please ask. Please confirm. Is it okay? Graph wise? Okay. So let's continue further. Now let's just talk about the next one. That is the stereochemistry of this reaction. Okay, so how about the stereochemistry? This is also very much important there. So what is the meaning of this point? That is a stereochemistry. You know, stereochemistry wise, obviously here we are not having any kind of SN1 and SN2, so no substitution. So basically we are end up with only one thing, that is double bond. So can you just tell me if I'm having a double bond, so what is the which kind of possibility, like which kind of stereoisomerism really we are getting? Option conformer, second option geometrical isomerism. What do you think if we are having that as a double bond? So is it which kind of stereoisomerism we are getting? Conformer or the geometrical one? Okay, what does the meaning? Yes. Okay. So is it like cis trans or ROS? Which kind of nomenclature? Cis or trans, right? So yes, GI, yes. So be noted now, GI is no longer only cis and trans. Okay, GI is no longer cis and trans. Okay, I will tell you why it's no longer cis and trans. So wait, I will tell you about this. Listen my point first of all. Okay, that basically we know typically if you're having a carbon carbon double bond, and let's say some CH3 group is connected this side, and there is a one more CH3 group connected this side. Okay, there is a some kind of hydrogen there, there's a some kind of hydrogen there, right? So in this case what you're observing, both the CH3 group connected on a same side. So yeah, I can say it's typically cis. Okay, what is new about this? Nothing, we already know, right? Okay, then second is going to be, if let's suppose I'm having a carbon and carbon double bond, and this is my CH3 and this is my CH3. And this is hydrogen and hydrogen there, right? So what is the second point here? If you have to observe that both the CH3 are trans to one another. Okay, cool, we know this. But my question to you right now, if let's suppose I'm having a carbon carbon double bond, and let's say suppose this is chlorine and this is hydrogen and this is CH3. So can you just tell me, is it cis or trans? Yes, is this cis or trans? Or am I right? I'm using this word cis or trans. At least like answer, is it cis or trans? Geometrically. Okay, okay, okay. Listen, my point. That yes, I'm assuming, like, ma'am, you can say, ma'am, both the hydrogen on the same side, and yeah, it can be cis, right? It can be cis if you to observe only the hydrogen part there. But no, as we already covered this point earlier, that if the group is different, so we have to give the priority. So priority wise, hydrogen atomic number is less as compared to the carbon, so this one achieve the first priority and this one achieve the second priority. And this side, this one achieve the first priority and this one going to achieve the second priority. And priority wise, both the priority group present on the same side if you to observe, right? So now the cis is this is no longer the cis really converted into what, that is a G. So we used to call this as a G now. So sometime in a question it is mentioned to you that there is some kind of GLK is given. So be noted, G is nothing. It is, you can say, updated version of a cis. Updated version of a cis is going to be the G kind of nomenclature. Simple. You have to simply assign the like priority there. One more. And then what is the new about the trans there? For example, if let's suppose I'm having a carbon and carbon, if let's suppose my chlorine is connected this side and bromine connected this side, iodine connected this side, and hydrogen connected this side. Now my question to you, like, okay, let me tell you what that is. Trans is going to be considered as a E type. E is there. So it is a E and this is G. Trans E and cis G. And now for this given question, what is this mention here? Maybe it is not visible. Let me just. Yes, please. This green one. I'm talking about this green one here. So yes, is this G or E? This one. Is this G or E? Yes, please. Okay, just give the priority and let me know. See, cis means G, okay? It means same priority group, same side. So G we are going to use. Okay, if trans, it means the priority group if different. So we are using E. So E, Z. Okay, okay, Aditya, okay. So let's see what is the correct answer for this question, really. So in this case, if you have to observe, like priority wise, I'm talking about the priority there. So how about the priority there? Chlorine and hydrogen. You know, chlorine is the more bulkier, or atomic number of the chlorine is maximum. So it's going to be the 1 and 2, right? And this side, bromine is larger. Bromine has a maximum atomic number as compared to the bromine. So this iodine and this is the bromine, second there. So in this case, observe both the same priority group. Both the same priority group present on the same side, that is chlorine and iodine. So what is it really? So it is still what? G. This is still G there. Okay, this is still the G there. Okay, because it's a cis, same priority group on same side. Okay, is this point clear? How to identify? Okay, let's solve one more question. Okay, one more, last one. Okay, what do you think about this? Take your time, 1 minute for you, and please answer this. This time, no excuses. Try to understand. Okay, Mike, this is for you. Of course, Abhyan, I will. Okay? Yes. Till then, everyone, you can solve this. Okay, let me just explain one more time, Abhyan. So listen, my point that first of all, that this is a carbon-carbon double bond, right? So in this case, in the previous question, what is happening there? This is my chlorine. Okay, this is my hydrogen, and this is the iodine, this is the bromine. So we have to assign the priority. If you don't know the priority rule, so you can check, I guess, third session. Okay, same, I guess, first or second, third have to be there. Okay, there we discuss the priority rule. So what does the priority rule said? Let me just give you a kind of brief. It's a CIP rule, that is the chain, uh, hence, and that preload model is there. Okay, so this is a different thing, we're not going to discuss about this. So what is this? That if you to observe, according to this rule, the first priority is given to the atomic number. Atomic number, it means that the first priority is given to the atomic number, which one has a maximum atomic number, so that then that one get the first priority. So this is my hydrogen and chlorine. You know, chlorine atomic number is 17, and hydrogen atomic number is 1 there. Okay, so 17 is maximum of the 1, right? Obviously, so means priority wise, I have to give the first priority to the chlorine and the second priority to the hydrogen. Case number 1. And the second one is what? Chlorine and bromine. Now we don't know the atomic number of chlorine and bromine, but at least we know that fluorine followed by chlorine followed by bromine followed by iodine. I know definitely that iodine has a maximum atomic number over the chlorine. At least I know this point, right? So in this case, you can say that iodine and chlorine. So which one has a maximum priority? The iodine and then the bromine in there. So you know that, look at this, that if you to observe the chlorine and iodine, first priority, yes, first priority, yes, same side, yes, both are present on a same side. Like it's like a cis. Okay, both present on a same side. So you can say cis is behaving like a Z. So it is going to be the G. It is going to be the G. Okay, is this point clear now, Abhihan? How to? Please confirm. If you're not getting, we can consider more examples. Yes, Anjana, you're right, basically. Okay, please confirm. Till then, let's back to the question. G. Are you sure about this? Okay. Okay, not an issue. Okay. So yes, let's try to solve the question. I guess it's enough time for everyone, right? So let's observe this. This is my double bond. Let me just observe this. Like every time, mark it. This is my double bond. We're going to check it for the double bond, right? So this side, the carbon. Okay, no, we're not going to discuss about carbon, hydrogen, anything. Simple priority we are checking. And this is bromine. So definitely, if you have to compare between a bromine and carbon, so obviously the bromine have the first priority and a carbon have the second priority. Okay, second case. In this case, if you have to observe, this is my chlorine, and if you are moving there, okay, it's a carbon, carbon again. So between chlorine and this carbon, which one have the first priority? Obviously the chlorine, and this is the second one, that is a carbon. And in this case, if you have to observe again, that first priority group on the same side. Look at this, this is my first priority and first priority group on the same side. So this is again going to be the G. Okay, I hope now the G and E nomenclature is clear for everyone. Okay, yes, very good, Sanjan and Hazu. Okay, very good, everyone. So that's it. This is all for this kind of, you can say, what we're discussing is ENG. So let's just back again, stereochemistry one, right? So in short, that here we're talking about the cis and trans, okay? So let's see that a kind of example for you. So this example is simply representing the dehydration, that is the removal of hydrogen, OH group is there. That is the what is that? Wait. Okay, this one. Dehydration of alcohol there, okay? We're talking about the dehydration means that removal of water there. So where was the slide? Okay. Yes, look at this. So this is my OH group. So this OH group has a lone pair attack here and the same H water volume is generated, and this is a formation of carbocation now. Second one. So in this case, after the generation of carbocation, since this is a type of alpha and beta elimination, if you don't know alpha beta elimination, please watch the previous class. We discussed already there. The carbon on which the positive charge is there, this is known as a alpha carbon, and with respect to this, the next carbon is going to be my beta. So this is alpha, this is beta, and this is also a beta. Alpha and beta. So it means we are in a search of beta hydrogen. Yes, we are in a search of beta hydrogen. So this is my beta hydrogen, this is my beta hydrogen, cool then. So who's going to participate? Like, let's see that what about the possibility there. So there's a two kind of possibility. Possibility number one, maybe this A is going to participate. Okay, maybe this A is going to participate. Or the possibility number two, maybe this B. Okay, one hydrogen is going to take place, you can consider this or that, it's not an issue. So A can be there or B can be there. So let's just use if A is going to participate. Let's suppose I'm using red color for the A. Okay, if A hydrogen is going to participate, so what is happening in this case, that the carbon, double bond carbon, it's a CH2, okay, and this is hydrogen and this is my CH2 and this is my CH3. So for the A we are going to get this kind of product. Okay, so how about the B? If we are checking for the B there, so if you have to proceed with the B, what is happening, that this hydrogen maybe, let's say, participate. So in this case, let's just use a different color. I guess it's not clearly visible for you. Okay, wait, look at this one. Okay, this one I'm talking here. So how about this side that you are having CH2 and this is my CH3 and there's a carbon carbon double bond and a CH3 and hydrogen there. This is a product number B. So now question be like, which one is major? Like A is major or B is major? Okay, then okay. If you don't know anything about the mechanism, okay, if you don't know anything about this mechanism, still my question to you, can you just tell me between A and B, which alkene is more stable? Which alkene is more stable between A and B? It's a very basic question of the 11th class. Which one is more stable? Hint for you. Apply hyperconjugation concept. How to check it? Yes, please. Um, yes, here we're talking about basically the acidic medium. You're right. Okay, has you? But wait, I can't say every time. Okay, there's a so many reason as well. So just for this class only, yeah, you can say B there. Okay, so you know how to identify this. We know everything. If you remember that this is my double bond, that is a group of discussion, that is the point of discussion, and there's a two alpha hydrogen only. Okay, there's a 2 alpha hydrogen only. But on the other hand, if you have to observe this point there, look at this is my double bond with respect to this carbon. How many hydrogen? 3. This carbon, how many hydrogen? 3. Total 6 alpha hydrogen is there. So wait, 6 alpha hydrogen more stable? Yes, B is more stable over there. And in term of chemistry, do you know what we are going to say them? That is the more substituted double bond is what? Sedgwick product. So it's a Sedgwick product. And this is what Hofmann product. So what is the meaning of this word Stadjev and Hofmann? Stadjev means more substituted double bond. Hofmann means less substituted product double bond. Okay, so observe this. This is the point there. That it's a minor, it's a major there. Okay, and if you have to compare between major and minor, so yes, wait, yes, this is the major one. Okay, this is the major one. And now my question to you, how many stereoisomerism possible for this? Right now, we are not talking about stereochemistry. We are just talking about selectivity, like major and minor. Okay, B is major. But how many stereoisomer are possible for this B? Obviously, I'm talking about cis and trans. Okay. So two there, right? So two there. Anyway, let's not waste their time. So cis and trans two can be there. So double bond. Okay, we can admit like butene is the correct answer. So cis and trans possibility have to be there. So this can be the correct answer. This can be the correct answer. But my next question for you, which one is going to be stable one, cis or trans? General. I'm talking about general. Please, cis or trans? Which one is more stable? No response. Trans. We know, right? Because bulky group, they are away from one another. So obviously they are going to be the stable one, right? Okay. See this? That repulsion, crowd. And in this case, they're anti to one another, less repulsion there. So we can say simply in this case, less repulsion. And okay, trans is generally stable. So what will be the conclusion? The conclusion is very simple, that I said generally trans is more stable over cis, because every time in chemistry general thing is going to fail, right? So more stable, you can say more stable than cis. Okay, cool. So let's quickly brief all the point that we just discussed in today's class. In the next class, the topic of discussion is going to be the E2 mechanism. Okay. So yes, if you are asking about the sessions already, right? So see, I'm not only explaining haloalkane or haloarene, right? First of all, we start with haloalkane and haloarene, then we discuss about SN1, SN2. Now we're discussing about E1 and E2. Okay, like this is how we're proceeding, so that we are not facing the same problem again in the other top chapters. So that's why we're considering the main topic here. Okay, I hope you're getting my point. So what is the conclusion there? What is E1? Unimolecular, two-step or multi-step reaction you can say. Carbocation is the determining step. Alkyl halide activity, tertiary, secondary, and primary generally follow the Sedgwick product as a major one. Okay then. Now, very much important question. Okay, last question of the class. Everyone please participate. And okay, it's some advanced question. Okay, so question said you are using this. Okay, this is nothing. Just for this class, you can consider this a base. It means the main agenda for this base just to take the proton only. Okay, now there is some options for you. What will be the correct answer for this question? Okay, so option number one. Okay, just try to solve this. 1 minute for you. Till then, I'm giving option. What you have to do? Okay, take a screenshot or something. Try to solve this on the next class so that I can write the options for you. Okay, just do this, please, everyone. Try to solve this. It's not like advanced questions, so it's going to be difficult. No, it's very easy. It's really very easy here. Okay, I hope you are done. So let me just give you the options now. So option number one. Okay, yes, please. This is the question. This is option number A. Okay, this is option number B. Just by using the elimination method, you're able to eliminate two options directly. Yes, please now answer. Which one is the correct option here? A, B, C, or D? Hi. Yes, please. Hi, sir. Anyway, please answer this question. A, B. Oh, I'm sorry. Yeah, this have to be C, okay? C, and D. Okay, Aditya, now please. C, A. Aditya, if you're saying C, it means what I'm explaining right now, like everything is just in vain, right? Hmm? See, we just discussed more substituted double bond is the correct case. So see, this is more substituted. No. Is it more substituted? No. So maybe the option number B or maybe the option number A is going to be the correct, right? Then how? Okay, Vivek and Sanjana. So yes, Aditya, you are right. I guess no, right? Yeah, it's phenol. It's pH. pH. Okay, maybe my writing is not very good. I'm sorry for this, but yeah, it's pH there. So now. Okay, 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 okay. So I admit, like, I'm getting this is the correct answer. Okay, B. Okay. First of all, if you have to decide between B and A and B, if let's suppose there's a no question for you, still my question to you, which one is more stable double bond? Okay, let's suppose I don't know anything about the question, but still I'm able to solve this. How? See, if you have to observe the priority, this is priority number one, this is priority number two. Oh, sorry. Opposite, I'm sorry. That is, this is my priority number one, this is my priority number two. And in this case, priority number one, priority number two. Done? Because this is carbon, this is hydrogen, obvious, it's a small in size. And the second one, if you to observe there, this is my one, this is my two, and then this is what, it's my one and it's my two. And yes, let me know. Okay, I'm not asking about cis and trans, I'm not asking about anything, look at this. The bulkier group, in this case the one priority group, are just opposite to one another, right? And in this case, that both, like, same priority group on a same side. So obviously, which one is the correct answer? Hmm? Still you're saying B. Okay, no, A is the correct. We just discussed that is the trans is more stable and more stable. Okay. Uh, Elimination. Yes, already done, Hazio. You can check it for session 2 or 3. Okay, we already covered. Yes. I hope this question is clear for everyone. So option number A is going to be the correct answer. Okay then. So that's it. This is all for the today's class. Done from my side. Any problem, any like doubt, please ask then. Okay, so, and this question will be a HW for you. It's going to be easy question, so yes, try to answer this question. Okay, this is HW for you. Yes, any problem, any query, please ask. Yes, please quickly ask if any problem you are having. Otherwise, let's end the class. Yes, you can check it for 2 or 3. Right now, actually, clearly not. Thank you so much, Jatin. Thank you so much, everyone. Thank you so much for everyone, everyone joining the class. Okay, thank you. Thank you so much. Okay, let's meet in the next class. And from today onward, I'm going to take the classes on YouTube only, okay? Because it is easy to handle everything here as compared to the meet. Okay then, thank you. Welcome, Sanjana. Thank you so much, everyone.